Our next example will be complex conjugation. We actually have a couple different rings that we can define complex conjugation on. I'm going to go ahead and do that just in C, and then I'll say how this might generalize. So what is complex conjugation? Well, it's defined as when you plug in an A plus BI, it spits out an A minus BI. So it's the negate the imaginary part guy. Let's go in and let's check it preserves, or let's check to see if what it preserves and what it doesn't preserve. So if we take, throughout, we're going to take two complex numbers. In fact, let me just maybe put up here in green that throughout, A plus BI, C plus DI are going to be two complex numbers. And so we need to look at iota. This is the iota symbol of A plus BI plus C plus DI. And we're going to have to compare that with iota of A plus BI plus iota of C plus DI. And again, we don't know if this is true. So let's put a cautionary orange question through it. On the left-hand side, we have to add first before evaluating. So we get A plus C plus B plus DI. That's the rule. And then on the right-hand side, we can actually go ahead and evaluate. So it's A minus BI plus C minus DI. And now that the left-hand side is in the form of a complex number, we negate the imaginary part. And on the right-hand side, let's see, we can associate the real parts. And then we have a negative B and a negative D, so we can pull out a negative I. And I'll put the negative in front and the I on the right. Are these equal? Yeah, these are equal. So we're gold. So that's preserves addition. Great. Let's now check preserves multiplication. So we have to ask if we multiply before plugging into iota, and if we multiply after plugging into iota, do we get the same thing? On the left-hand side, the product is the product inside of iota is AC minus BD plus AD plus BCI. And on the right-hand side, oh shoot, I missed my question. This is a question, of course. On the right-hand side, we have, we just plug it into iota first, we get A minus BI, C minus DI. Cool. And then iota just negates the imaginary part. So on the left-hand side, what we're going to get is AC minus BD minus AD plus BCI. And then on the right-hand side, we multiply it out, right? So we get AC and then negative BI times negative DI is positive BDI squared, but I squared is negative 1. And then our cross terms are going to be negative AD and negative BC. So are these the same? Yeah, if I pull out the negative, they're the same. Great, so it preserves products. And now we need to check that it preserves 1. So the 1 in the complex numbers is 1 plus 0i. So let's compute iota of 1 plus 0i. That's 1 minus 0i. But 1 minus 0i happens to be the same as 1 plus 0i. So it preserves 1. So what we learned from this is this complex conjugation, which I'm calling iota, you can call it whatever you want, is a homomorphism. In fact, complex conjugation geometrically is a reflection in the real axis. So in fact, iota is a monomorphism. And since every complex number is a reflection of something, iota is an epimorphism. That is, this is a one-to-one and onto homomorphism. Since it's a monomorphism and an epimorphism, and it's an isomorphism, since it's an isomorphism from C to itself, it is an automorphism because the domain and the codomain are the same thing. Great, fantastic. Let's do, and so again, if you were to say which of these is it, and here you would go for the strongest one, you would say, oh, it's an automorphism. Because automorphism implies all of those other ones. All right, so where else does complex conjugation make sense? Well, usually whenever you have a subring, for, well, I'm not going to say any. Let's not use such strong words, but for subrings of C. And examples are we encounter the Gaussian integers. So if I take iota of a Gaussian integer, we get a plus, let's write it like this, negative bi. And since, a, b, are in z, we get the a negative b are in z certainly. So if you plug in a Gaussian integer, it happens to spit out a Gaussian integer. And so iota is a well-defined map from the Gaussian integers to the Gaussian integers. Ah, we just checked it was a homomorphism, and in fact all of those other properties are true as well, and it will remain an automorphism. Another set that we encountered was sets like z adjoins square root of -2. Sorry, I mean subrings, not sets. Oops. And z adjoins square root of -5 just recently. And iota makes sense here too. And by makes sense, let me use the proper words. Iota is well defined on these rings as well. In fact, it's an automorphism of these rings. So it's the strongest of all of them. So we actually have now a wealth of different automorphisms, in particular homomorphisms, and these ones come from complex conjugation. We're going to continue doing examples in the next video.